Tangibilisco here from a globular cluster somewhere in an unknown galaxy, in an unknown universe, in an unknown set of universes, in an unknown thought kingdom, bringing you a presentation of something very simple that every mathematician should learn early, and that is the three-dimensional Cartesian coordinate system. Now, what do we mean by Cartesian? Well, first of all, the word Cartesian comes from René Descartes, who presumably invented the system of coordinates such as the one you see here. This is a three-dimensional Cartesian system. Now, in order to be Cartesian, a coordinate system has to have equal increments along each axis that represent equal changes in value. That is to say, the axes must all three be linear, x, y, and z. These axes must all be linear, and they must all have the same general size, so that, for example, if you have something that's 2 by 2 by 2 units, it's going to turn out to look like a perfect cube when you draw it, not like some sort of a distorted object that would result from increments of different size on different axes and all of that. It has to be that way. And there's something else that you need to know about a three-dimensional Cartesian coordinate system. A system like this is usually employed to render z as a function of x and y. That is to say, a two-variable equation with a third variable, a two-variable function, I should say, with the result being the third value z. So f of x comma y equals z. And there's another feature that a system like this has to have. Notice that if you go out positively along the x-axis and positively along the y-axis and positively along the z-axis, that they are oriented a certain way, so that, for example, if you consider this east, this straight up, and this straight at you, which would be south in this example, then the positive x-axis goes east, the positive y-axis goes north, and the positive z-axis goes south. So that what you should get is this particular orientation. If you flip one of the axes around, say if you were to make these values of z negative and these positive, you would have the wrong kind of orientation to the system. What you should generally expect is this particular relative orientation of the axes. Imagine all three axes are such that each one of them is at a right angle to the other two, and they all intersect at a single point representing 0 for x, 0 for y, and 0 for z. Then the positive x-axis you can consider to go east. The positive y-axis you can consider to go straight up. And the positive z-axis you can consider to go straight south. That's important. All of those considerations are important for a coordinate system to be a true 3D Cartesian system. So that's a little bit of definition and a little bit of rigor for you early on as you learn your analytic geometry. That is to say, graphing functions in 2 and 3 dimensions. What really gets fun is when you get into more than 3 dimensions, so that you cannot visually render the coordinate system in a perceptible, understandable form at all. You have to have a mathematical imagination. Something that if you have, you know you have it, and if you don't have it, you know you don't have it. Chances are if you have it, you love math. Chances are, if you don't have it, not so much. But in any case, you can always escape to a globular cluster in an unknown galaxy, in an unknown set of galaxies, in an unknown universe, in an unknown set of universes, and you can name it for yourself. How about calling it meaningless? No, how about calling it Cartesian? Stan Gibilisco signing off, saying so long for now.